Alright guys, let's talk about Banach's fixed point theorem. And the theorem is all about a value which exists unique and happens to be the fixed points of a function that is contractive in nature. So we say value x is such that f of x is equal to x is a fixed point of that function. So the theorem guarantees that x exists, it is unique, and it only happens if f is contraction. Now, what is contraction itself? A function f is a contraction given a constant k between 0 and 1, that there exists 2 points in the metric set x such that f of x minus f of y is less than k of x minus y. Now, for what we have put down here, we can put it in practical terms by giving one example of a function that fits the fixed point theorem, both contractive and as a fixed point. So let us use this example. So you have f of x now. Example. A function f of x is equals to say 0.5 x plus 3. Now, we want to show a particular thing, that this particular function has a fixed point. That is our first attempt. Does it have a fixed point? Yes, it is possible. All that we need to do is what? Is to ensure that this function then results to what? To x, which is the fixed point. And how do we do that? We solve this expression from here to here. Then you have what? 3 equals to x minus 0.5x. And that is what? 3 equals to x. Rather, 3 equals to what? 0.5x. So that your x here, when you divide both sides by 0.5, your x is equals to 6. Now, tentatively, this 6 right here is the fixed points. It's tentatively our fixed points. Now let us introduce a contractive property. Of course, this function must be contractive before we can accept this as a fixed point. It's okay. Let's try that one. So let's call it f of x1 is equals to 0.5 x1 plus 3. And let's call our f of x2 now. F of x2 0.5 x2 plus 3, so that when we put them in this function right here, we'll come back here and put them in this expression. In this expression right here, put it in the expression right here, you have this. You have this. You have your f of x1 minus f of x2 to be equals to, now what do we have for f of x1? We have 0.5 x1 plus 3 minus, now put a bracket, 0.5 x2 plus 3. And when we work this out further, okay, you will have your 0.5 x1 minus 0.5 x2. Of course, what happened is that these two takes themselves out by the time you expand the brackets. So you have this, and that translates to this now. That translates to this. So you have what? 0.5, factorize 0.5, leaving what it was x1 minus x2. And it makes sense because from what we have here, it implies that k is equals to 0.5, which satisfy the contraction condition that your k must be less than 1. And that means this function right here has a unique fixed point at 6. Okay? Now let us try this out with a normal value. Let us try that if truly it actually converges to the unique fixed point 6. Now we try some random value starting from 0. So we say, okay, let our x naught be 0, a random value. We slot in x naught here, so do f of x naught, which is 0, is equals to 0.5 into 0 plus 3. Yes, this will give us 3. Okay, so we take it a step further, is 0.5, so the half of 4.5 here equals to 0.5 into 4.5 plus 3. And then when you work this out, you have 0.5 times 4.5 here plus 3. You get 5.25. And when x3 now is 5.25, our initial answer, so you have f of 5.25 equals to 0.5.25 plus 3. When we work this out, you have 0.5 times 5.25 plus 3, and you got 5.625. So when we keep trying this, let's try this for the fourth time. x4 equals to 5.625. So you have f of 5.625 equals to 0.5 into 5.625 plus 3. And when we do this also, 0.5 times 5.625, we get 5.8125. We notice that these values keep tending towards the fixed point 6, meaning that what it is converging towards 6, and which shows that what this particular function actually has a fixed point, and the fixed point is unique by the contraction property of the function itself. Okay, what if we try another function that actually does not converge? And once it diverges, then of course the Banach fixed point doesn't really occur in that kind of function. So let us call it example 2. Yeah. So example 2. Example 2. Yeah, the function we are working for, example 2, f of x. So is equals to 2x minus 5. Okay. Our first step is to show it that this function has a resemblance of a fixed point. So we equate it to what? To x, same way. So that means we solve this now. We have 2x minus 5 equals to x, and that would be minus 5 equals to x minus 2x, minus 5 here equals to minus x. Invariably, x is 5. Okay, so by tentatively our fixed point here is 5. But let us see if all our other points will converge towards this. But first, we need to try this on contraction. So I'll move this up a bit. So let's put it right here now. So we have, for the contraction, you have this f of x1 minus f of x2, right, is equals to, what do we have? We have 2x1 minus 5, yeah, minus 2x1 minus 5. Okay, and then if you work this out, yes, this is 2, sorry. This takes this out by the time you expand the brackets. Okay, becomes plus. So what is left is just what? 2x1 minus 2x2. So take out the common value, which is 2x1 minus x2. Now at this point here, you have a value for k, which is 2, which is not less than 1, which simply means that what this particular function does not satisfy the contraction property, and therefore by extension all other points diverges. So it has no unique fixed points. So, and how do we confirm that, or doesn't support the Banach theorem? We can confirm this also using values. Okay, we can use values in this respect also. Say for example, start with x naught equals to 0, and that gives us what f of 0 right now equals to 2 into 0 minus 5. This will be minus 5. Now all of these points we're generating will not converge to 5, which is the identified fixed points. Then for x1, which will be minus 5, try this now. F of minus 5, you have 2 into minus 5 minus 5, and this becomes minus 15. Now if you try for x2, of course, even with that value, we already know that we are tending towards a diversion, a divergence sequence. So you have a minus 15 equals to 2 into minus 15 minus 5, and then when you work this out, you have minus 30, that's minus 35. So eventually these values are going far away from 5. You can start from any points for your x naught. Eventually you notice that what the values are tending away from 5, maybe from the positive side or from the negative side, will be the same thing. Then this shows that what this particular function does not satisfy the Banach fixed point theorem. And that is this for today's class. Thank you very much.